Thank you for that introduction. Yeah, just a little bit of background on PS, Puget Sound Institute, and then on the project. Much of the work, as Gordon has said, that the Puget Sound Institute does is around Puget Sound Partnership Recovery Goals. So that's the sister government organization to ecology. And what we do specifically is they're working on the policy and applied science synthesis. The program of work that I'm actually presenting today is with the Science of Puget Sound Water Quality Project and Program, and that's funded primarily from King County. And you can find out more about the various workshops, which there's many different authors and contributors, including some people in the room here that have presented, and we have all of those recorded and available through the website, along with some of the materials that you see today and other modeling work that's being done, and outreach materials as well. So you might be wondering why I put one of my favorite pictures of getting stuck in the mud in East Africa in a tidal estuary here. Well, for two reasons. The first is I was putting this together and realized I have no good pictures at all of field work in Puget Sound, which is really disappointing, and I hope to correct soon. And the second is just to point out and remind myself of some of the collaborations that I was afforded and the opportunities with marine research institution individuals and those in fisheries and government in coastal East African countries, and some of the island states. And just, I would really appreciate making the connection with folks who might be interested in working with them. And I haven't been doing that much since coming here. So I'm really looking forward to that, particularly around student exchange. So back to Puget Sound. I was asked to come and provide a bit of background and an update on some of the science around nutrient reduction strategies within Washington State. And so I will present some of the recent modeling and uncertainty analysis that we've been involved with, and what that tells us around the confidence in model application that's being used for decision making in the state. I first will focus on some of the target areas and times of the year where we have lower dissolved oxygen, where it's modeled to be lower, and what we understand around the model skill of those particular outputs that are being used. Then look at the potential further sensitivity analysis and uncertainty analysis that has been identified that might improve confidence, give some context on how those target metrics, and so that's dissolved oxygen for this particular model application, how those target metrics are used, particularly in the nuance of the model-to-model application that's used here in Washington State, and then conclude with some additional lines of evidence for quantifying impacts on biology, and particularly for quantifying dissolved oxygen exposure impacts. So first, something on the problem faced and the application of the model. So as you're all aware, Puget Sound is part of the Salish Sea. It faces challenges of recovery of orcas and salmon and the ecosystems that support it. And since I've come here, I'm not sure if I can use this little cursor. Let's see if this works. There we go. I've often heard it referred to as the tail that wags the dog of the Salish Sea here. And I think that's a pretty interesting thought when you think about the efforts that are put into it. It has a huge tidally driven flow that comes over Admiralty Inlet here in the sill, even larger flows coming in with connecting seasonal ocean upwelling. And let me just go back. There's one thing I'd like to, yeah, okay, great. So, but it does have sections that are fjord-like, stratified and naturally prone to what we expect is natural low dissolved oxygen or hypoxia, and I'll refer to that in this talk as less than 2 milligrams per liter, such as Hood Canal, as you can see in orange here. And there are many embayments and inlets that are shallower, they've got longer residence times, and therefore they're more susceptible to anthropogenic impacts, both toxics and nutrients. even though the main channels that are connecting them are well flushed. And so some examples here that we can talk about today, if you follow South Sound here, we've got Case and Car Inlet, and also Pen Cove here in Port Susan. So even though these systems, the Puget Sound itself is quite different overall to classic coastal plain systems such as Chesapeake or some of the ones that I've worked on prior, the subsystems within them are more prone to these same anthropogenic impacts. And therefore, there's been an extensive program of nutrients, and we're faced with this challenge and effort and interest and national funding to look at this particular question. It's a bit of a, if you like, a wicked problem that we're facing, which is how do you quantify change in eutrophication impacts on marine life as you're looking at projecting these nutrient reductions and then quantifying if they've had any impact. So in Washington State, the Salish Sea model is used for this regulatory compliance. I won't go over the details too much of the various modeling efforts that we have here. The model, just pointing out, first of all, there are multiple modeling efforts that have been quite extensive. For example, Parker McCready's work with Live Ocean, and the Salish Sea Cast in University of British Columbia, and the Salish Sea model, which has been developed by Tarang Kangonkar from both PNNL and then now as director of the Salish Sea Modeling Center, which is also housed with us at Urban Waters in UW-Tacoma. I will point out that the Department of Ecology has contributed significantly to the advancement of this modeling effort using the Salish Sea model, particularly on nutrient inputs. And it uses the outputs within Puget Sound waters and the waters of Washington State for the interpretation of the Clean Water Act. So it's fairly unique in using a model-to-model approach for setting effluent limits. While other states use models to set limits using a model, they might do that, then they would use a direct measure for compliance. So Washington State, in this case, uses both. It uses a model-to-model for that compliance, and that's where it's unique. So that is to say, any scenario of reduction of current conditions are then compared to what you'll hear me talk about as a reference condition, which represents the pre-anthropogenic nitrogen loading for Washington State. And this is driving historic billion-dollar investments that are expected to take decades to implement. So a little bit more on this reference scenario, as I was asked to go into a little bit more detail on this. The reference scenario is best estimate of pristine conditions, if you like, where nutrient loads from the watersheds of the state of Washington before any anthropogenic influence associated with a Western sediment. The reference condition is calculated for a specific year, and it's compared to a model current condition from measured data from that year. So if we take 2014, which is one of the model year runs that's done, there's 3 model years runs that are used by the state for this purpose, 2008, 2007, 2014. So by taking that as a comparison to it or any other proposed scenario estimating a reduction from that. So for example, if you were to take 50% loading of wastewater treatment plants for 2014 year, the delta difference between this magnitude is then used as the metric that's used for evaluation, and then a threshold is used to determine if that delta difference indicates degradation or impairment, or what it's called non-compliance here. So this is currently set to 0.2 milligram. So that's the difference of a reference to the current or any scenario of 0.2 milligram difference. This approach is under revision by request of the EPA, but the results presented here and what you'll find published are all based on this. Okay, so to summarize, the reference condition is effectively the current condition with the removal of all Washington State wastewater treatment plant and rivers to get a pristine level. Everything else is kept the same, and we should note that that includes then nutrients that are coming from the ocean, as well as Canada, including Fraser River. And just to give you some perspective on this, the wastewater treatment plants and rivers account for about 10% of the nitrogen that enters Puget Sound. And then to summarize on the current metrics used, if there's a cell from the model that has an area, has an associated area, and it's triggered non-compliant, if any layer within that cell for any hour of the day reaches that threshold difference, that gets triggered as non-compliant. It adds up to a day towards 365 days that's potentially for that cell or of that particular area. I have more on these and other ways we've looked at using additional lines of evidence on it, but I think that gives you the basics of it. So what does that look like? Well, if you look at this model to model output, we could take an example from Quartermaster Harbour here at the 10th layer, so at bottom level, and you can see the existing scenario or current conditions for 2014 in red, and then the reference scenario, which is higher here in blue. And as you can see that it's during the month of August and September where there's the greatest difference between these two. And so that delta difference is shown here in green on the bottom figure throughout the year on the x-axis. Whenever that reaches a threshold of a 0.2 difference, then it triggers a non-compliance. And so we have here, I think it's about 100 points or 100 days where that non-compliance is occurring that would contribute for that particular cell. So now let's look at some of the results here. This animation shows the dynamics of minimum dissolved oxygen across the Salish Sea and Puget Sound. We can see that the waters of the straits are generally lower, shown in orange here, than, of course, the channels of Puget Sound, which are shown in blue. And that is throughout the year, starting in Hood Canal and Bellingham Bay in around August. There are some areas that are less than 2 milligrams per litre, which will be shown, as we're talking about in hypoxia, in red here, at least within one layer of the water column. Then it's followed by Bellingham Bay, I said Whitby, and then South Sound, Case and Carr Inlet that we were talking about, and then within some of the ends of these terminal inlets in the main basin. By about October, those lower levels of dissolved oxygen are only seen, but do persist within Hood Canal into the winter. This map represents the maximum area extent of hypoxia for 2014 on the left, and then the reference on the right. And you will see more if we look at some specifics of, say, Bellingham Bay in the north, or particularly at different times of the year for South Sound. But it's just really to reiterate the value of going beyond looking at a minimum trigger value. That we really need to look at specific shallow water embayments where we've got these impacts. These systems are geomorphically quite different, and they're flushed. In these other parts of the system is flushed so much more, and so we really need to focus on these particular places and at these times of the year if we're trying to look at impacts. So towards this, in the project, we had a group, a model evaluation group of experts that were experienced in working on various estuaries that are impacted by low dissolved oxygen, and particularly those that are thought to also have naturally occurring hypoxia. And they were really focused on the Salish Sea model's application for nutrient reduction strategies in the state, going over the published skill and error analysis that's available and looking at where there might be ways to improve wider confidence in this application. So that we were able to look specifically at the error analysis relevant to these areas of concern and times of a year where there was a modeled impact. And so here on this figure on the right, we've just labeled these 16 areas that are specific, of specific interest. Within that, from the published literature, there were 28 sites with CTD casts that also had dissolved oxygen, where we could look at the model area analysis and really focus in on what the results are for the parts of the model outputs that are being used. And these were from the years 2006 and 2014. On the left here, we have an example for case inlet, and you can see we took the best and worst case root mean square error on each just to try to get a range there, but only where there was at least 3 months of the year that were covering the time of the year when there is actually low dissolved oxygen. And this output here is to show the model, what it looks like in terms of the extent of these 16 areas of concern. And I think, Gordon, you did mention that not everything was going to come out very well. You can't see the land here, but it looks pretty good on my one. But if we can imagine that this is South Sound over here. Let me see if I can get the cursor over. There we go. So this is case and car inlet. That's a little bit of Hood Canal here. The main point of this is just to show that when we model where there's impairment for the state for 2014 in the publications that you'll find online, there's 341 kilometers identified. This is basically cookie cutting them to show you which cells they are, right? So this is showing, this is the extent in case inlet, car inlet, and here's the minimum dissolved oxygen overlaid for that. So you get a bit of idea, but that's the minimum for the entire year. So any hour of the day within any water column layer for each of those cells. The point of this is really to show this is where we're taking these CTD casts from. So and these outputs. Yes.
Sorry to interrupt, but so the models vertically stratified at like what resolution? And I guess I'm wondering because they'll trigger one of these even if it's say the bottom 1 meter of the water as opposed to a section of the water.
So are you saying how many layers does it have?
So this shows up as deep red, a single.
That's the way it's being used at the current. Yes.
And you don't integrate at all. So
no. So it's a very good point, and that's hopefully the point of a bit more discussion afterwards. This is the way that the state is using the interpretation of the Clean Water Act, saying that with any layer within the 10 layers that are used by the model. So the model actually does output the 10 layers, and you'll find that most of the top layers are not having that problem of low dissolved oxygen for most of the year. But the way that it's being interpreted at the moment is it's triggering this roll up. So what we did in all of the modeling analysis we did, because we're not doing it for a regulatory purpose, is we did a volumetric analysis, and we just tried to at least account so that every hour contributed in terms of time and then each in terms of space. But yeah, it's a bit of a challenge, isn't it, to think about it. So yeah, I think I can finish on this. The point is that those sites that we've been talking about, they're within these areas only. So we limited it to where the state has identified a potential difference or impairment between the existing and reference. And I should point out, I got plenty of material if we want to talk about it after on how that's calculated and some examples of using a volumetric calculation instead. So let's look at some of the results from the model evaluation group. I mean, this is really just based on what literature they had available, right? So there's been extensive publication done on each of the versions of the Salish Sea model that Terang developed. And most of this was for domain-wide analysis. So in all cases, we can consider that the Salish Sea model performs at least as well as other models that are used for nutrient reduction strategies. It has when we look at the domain-wide scale, it has around 1 milligram dissolved oxygen root mean square error. It does similarly well for temperature, tides, and some of the physical parameters that were done in earlier versions. And this has been pretty consistent throughout the different versions. The version that's used by the state is a single year run, and that's for 2006, 2008, and 2014, so 3 years. And this is a calendar year, so it goes from January through to December. Of those, the 2014 model run was the most advanced version. It had better ocean forcing and had a root mean square of 0.98 milligrams per liter dissolved oxygen and a relative error of 11%. So what that actually suggests is that when we take all of the points that we use for the error measured to model calculation for root mean square error across the sound, we're really looking at inputs that are saturated oxygen around 10 milligrams. And so that just drives us to the question of, well, if we're looking at the particular outputs that are lower dissolved oxygen, what is it for those specific embayments? And for Hood Canal, where we have the lower dissolved oxygen below the peak decline. Now, we didn't have access to the underlying data sets, but just taking the 28 sites that I mentioned earlier and just looking at an average of those root mean square error, it's 1.64. So it's above what you saw earlier for the domain-wide, and it's a range of around 1 to 3 milligrams per liter for dissolved oxygen. Similarly, looking at the bias for those 28 sites, there's generally an overestimation. And so for the 20 that overestimate, you can see to the left of this histogram here, the mean is around a 0.75 milligrams per liter overestimation of dissolved oxygen. The predictive power, when we look at the R squared as expected, is better for those areas that had larger and lower dissolved oxygen than those that are smaller. Okay, a little bit on the model metrics and the way they're used. So we found that they were quite sensitive to the threshold that's applied in this particular model-to-model comparison. The results presented here are the maximum difference in daily dissolved oxygen between the current and reference condition that we've been talking about for non-compliance in 2014. So the total area calculated and published is 341 kilometers. And all we've done here is simply bin that data across the x-axis with the magnitude of change between the current and reference. Now, regardless of whether the state uses the 0.2 threshold or a different approach to the calculation, I think this is relevant to show some context for where the model error presented earlier is in terms of the outputs that are used. So for example, it's for this first bin here on the left, it's 42% of the non-compliant area calculated is between 0.2 and 0.3, so quite close to that threshold. The model evaluation group had a number of specific recommendations for advancing the understanding of uncertainty and generally just more advancing the broader model development and regional coordination. And these will be in the report and we can go through them, but I think a couple that are pretty important to highlight here are just looking at more process-based investigation of error, using particularly the newly available data that's come about since the buoy data. None of this continuous data has yet been used. It's been used qualitatively, but hasn't been used quantitatively, which would be far better than some of the CTD data that we showed here. Particularly on the years, there's the opportunity to move from the discrete years with a hot start, cold start approach that's used to make it work for 2006 or 2014. And those are the years that were used for model calibration as well. And consider some of the opportunity where Terang Kangongkar's got the newer version of the model that actually runs over multiple years. And last, second to last here, quantifying the interannual variability and sensitivity. And what does it mean by using these particular years when we look at a longer time scale And I think there's a real opportunity there. And lastly, there is what was raised by the marine water quality implementation strategy, scientific advice, and some of the folks have been involved with that, identified that there's really some questions around how uncertainty is propagated with a model-to-model comparison. And there really wasn't enough information to make further assessment by the MEG on that, the model evaluation group. It really needs to be explored. Okay, I won't go into more of the broader recommendations, just to say that really an ensemble modeling development is the one that's lauded as the gold standard elsewhere, and Parker McCready's work and the work in University of British Columbia with these other models is really working towards that with some collaboration. And that really we need to look at the data access to it, not just the data access to the validation data sets, because obviously I'd be presenting something quite different if I had those available, but it's to make sure that these input data sets are shared across these modeling efforts. Lastly, on coupled, measured, and model analysis, there really is an opportunity now to look at quantifying multiple stresses, eutrophication, climate change, and fisheries, sustainable fisheries. And towards that, we are excited now to be involved as PSI with others to look at the development of new model metrics that could help us better understand species vulnerability to change, particularly with lower dissolved oxygen, and consider these as additional lines of evidence. The opportunity here is really to go from a trigger of low dissolved oxygen that I've spent time explaining is the way that the model output is being used now, to one that quantifies duration, frequency, return time, and then gets towards a risk-based or vulnerability approach, as has been used by Tim Essington's work that we've been looking to make these model outputs available for, and similarly for Marta Satula's work in California, which is used for a regulatory context to look at then metabolic index and habitat thickness or squeeze. Marta, as well as Tim, presented at the series of workshops that we had, and these are all available online, as well as a couple I've put here that really focus on modeling and monitoring efforts as well. And they range from isotopic and sediment trap studies to historical perspectives on nitrogen loading through to satellite investigation of phytoplankton change. So yeah, please, in many of these cases, they're actually looking for collaboration at a cross boundary from British Columbia. And so please get in contact either with those folks or and we've got Marielle as well here from PSI, who's been coordinating some of the stakeholder engagement parts of these. So in conclusion, some key takeaways. We can see that the target areas and times, if we look at the particular outputs of the model, have a larger error and bias. This just really indicates the opportunity to focus further skill analysis on a subset of the places where there is low dissolved oxygen. There's a number of steps that the model evaluation group identified for sensitivity and uncertainty analysis, not least the intraannual variability and multi-year runs and the availability of these measured data sets. And then in terms of target metrics and the way they're used, the small difference between the model-to-model results really shows some of the sensitivity in the current application. And then lastly, for future development, there's a great opportunity to use some of the existing model outputs coupled with field studies to really get at biological impacts now that we've got through the stage of work, particularly dissolved oxygen exposure metrics. And so on that note, I bring it back to that wicked problem that the state's facing, and that selfishly ask these questions. What further approaches could we be using to quantify change in biological impact over time that can use and build on these modeling efforts? And I really do look forward to discussion on what biological monitoring activities and data sets could be coupled with this. So I will open it